Okay, hi everyone. My name is Ben Mazurel. I'm an undergrad student at UVic, and I am the ADCS lead. I'm here today to present the ADCS Phase 2 review, pre-PDR. I'd like to give a thank you to Bernardo Sabino, Bernardo Lobo Fernandez, and Luis Romero for all of their work on this presentation and on the ADCS system as a whole. And of course, big thank you to Professor Suleiman for overseeing this project. So starting off with our stabilization strategy, our mission requirements were based around three major things. We needed nadir pointing, we needed a pointing accuracy error of below 10 degrees, and we needed an attitude estimation error of below 2 degrees. So based off of those numbers, we conducted a study on the possible ADCS architecture using the SMAD book. The strategies we considered were a gravity gradient. That ended up getting rejected because of the deployable boom requirements. And we also considered 3-axis reaction wheels. However, due to the small nature of ORCASat, that was rejected due to the volumetric and the power constraints. It just wasn't going to be feasible. So what we decided to select instead was a momentum bias with a 3-axis active magnetic control. So it was the only viable option given our space and power constraints, as well as the requirements of the mission itself. And then this stabilization strategy was validated using a model-in-loop simulation using MATLAB and Simulink, which we'll get into. So the requirements of the stabilization strategy itself, we had a sensor suite, and according to SMAD, for a pointing accuracy over 5 degrees, the magnetometer plus the sun sensor works. However, between a sun sensor and the Earth horizon sensor, we rejected the Earth horizon sensor due to sun size constraints, so we went with the sun sensor instead. For actuators, we decided to use in-house manufactured magnetorquers due to the low cost and a Hyperion momentum wheel. For sensors, for estimation, we're using 4 different sun sensors for the attitude determination, gyros and magnetometers for attitude determination, and the gyros are being used for the measurement of the angular rates of the satellite, as well as a GPS receiver. For ADCS estimation, we're using a CG-GAU and a Kalman filter, CG-GAU being a constant gain geometric attitude observer for rough and quick estimations of our initial estimations, followed by the Kalman filter for more exact and precise estimation. Taking a look at the block diagram of the ADCS here, you can see at the top, we start with our sensors. So these are the sun sensor, magnetometers, the gyros as mentioned, as well as the GPS. The GPS is fed directly into the Orbital Propagator, which produces the environmental models below, including a sun vector, the Earth magnetic field, which is based off of the WMM model, and atmospheric models. That then is fed into attitude estimation as well as those sensors above. With attitude estimations, as you can see, we have our MECF sensor, so the Kalman, as well as the CG-GAU, which then feeds into attitude control. Attitude control, the algorithm used is largely based off of whether or not our satellite is tumbling or not. If it is, we're going to use our detumbling controller, which is a B-dot controller. Otherwise, we're going to use a pointing controller or a PD, proportional derivative controller. Then the control quaternion that is produced as a result is fed into our actuators, which we use the momentum wheel and the magnetorquers as previously mentioned. The model-in-loop simulations produced very promising results. As you can see, using the detumble B-dot algorithm, we achieved stabilizations below 10. And the convergence occurred in usually under 2 orbits. For attitude determination with the Kalman filter itself, stabilization below 2 degrees typically occurred in under 3 orbits. Now with pointing controls, so the stabilization below 10 degrees, convergence would occur for us in 30 to 40 orbits. Taking a look at the ADCS hardware, what's central to this is our use of the TMS 570 chip. There's three major connections to this. We have our backplane, our debug header, and then an assortment of magnetorquers, sensors, and memory. The choice of the TMS 570 was one based on the fact that the CD&H team also uses it. We have previous experience with it working on Hamathco. It's well proven safety MCU with some flight heritage. So taking a look at the connections to this, as you can see on the left-hand side, we're connected to our satellite's backplane. That involves two I2C connections, which feed into our sun sensors. We're connected to the OBC via the backplane on a CAN bus, and then we also get our power from the backplane via 3v3 and a 1v2 regulator. Our debug header, which is used for our testing, uses UART to send data out and JTAG to write data in, as well as we have our reset pin through there, which includes a watchdog and voltage supervisor. Now moving on to the individually connected pins, we have three H bridges which lead into current monitors and finally magnetorquers on the bottom there, as well as a momentum wheel which is fed in via I2C. Then on the right-hand side, we have our three IMUs, which are fed via SPI buses, a temperature sensor, which is connected via I2C, and finally we have RTC A and B, as well as our MRAM and ECC flash, which are all connected via SPI. As for actual hardware, our actuators, we're going to use momentum wheel and magnetorquers, as mentioned before. We've decided to go with the Hyperion RW210, which has 3 micronewton meter seconds of momentum storage. According to the SMAD, our mission requirements require 8. However, given previous missions and the fact we're using magnetorquers, our MIL simulations verified that it's possible to just use 3. Therefore, that's the wheel we went with. Going into the magnetorquers, we're going to be manufacturing these in-house, most likely coiling them in-house as well. They've got a 1/4 amp meter squared, and SMAD shows that the coils should use about 0.06 amps meter squared to counteract the disturbance torques we have, so we have quite a bit of breathing room within that, which is actually a factor of 4, and the hardware team is quite confident that we are going to be able to produce that dipole moment, and again, that will be produced using the hardware unit tests. As for sensors, we have 3 major sensors. We have sun sensors, the magnetometer and gyro, and the GPS. Starting with the sun sensors, the decision to make this over the Earth horizon sensor was based off of effectiveness. Using the design procedure that was described in the SMAD book, the sun sensors with approximately 1 degree of pointing accuracy are sufficient to achieve our desired determinant accuracy of 2 degrees. To achieve this, we're using the Hyperion SS200 with a 100 Hertz frequency. For our digital sun sensor, it's got 55 degrees of view, and it's quite cost attractive, which was big for us in terms of our budget, while also meeting the requirements. As for our magnetometer and gyro, the sensitivity of the magnetometer would have to be a very similar position to the world magnetic model that we're using to model the actual magnetic field, the uncertainty of that. Whereas the gyro must also sense the typical range of the angular rate of the CubeSat, so it's got to fit within what we expect our angular rates to be, and we're going to be integrating them as a single part. Therefore, we're using the STLSM90S1, which is a magnetometer and gyro combined into one. Again, it's the most cost-attractive requirement-fulfilling sensor we could find. As for the GPS, really the only one our budget could afford is the Novatel OEM 719. It allows us to initially get our coordinates and should be effective for the mission requirements. Now we're going to take a look at ADCS software. We've got about 10 people on this team, so it's a nice, large, and well-coordinated team. We've made a lot of really good progress leading up to PDR here. So the philosophy behind our software is based around 3 major rules. We want our software to be accessible, verifiable, and modular. When I refer to accessibility of software, what I'm referring to is the documentation and ease of understanding. So when we have new members, they can easily be onboarded, so we can quickly expand our team without having to waste a bunch of resources on teaching people how to do things so they can get up to speed quickly and help the team out. As well as we want all members to be able to understand all parts of our software library. So it's really important that everything is documented, so that way you can easily hop between different parts of the subsystem, like the controller, the estimator, the operating system, things like that. And as long as the documentation is there, you can quickly understand what's going on. We also want our software to be verifiable. So basically what that means for us is defining the requirements and defining what can be tested, what shouldn't be tested, and we want those to all conform to specific logical standards that we've laid out in our README and our software standards. So that way all of our software is uniform and conforms to the standards that we need for flight readiness. The final part of our software development philosophy is modularity. Basically what we mean by that is we always want to start with the baseline ground, the foundation of our software libraries, things like that, and work our way upwards. So that way we don't waste a bunch of time changing things as we go on. We instead want to establish the fundamentals like our math libraries, our matrix libraries, the operating system fundamentals before we start to build on that to create the full software suite. A lot of our software is domain-driven inspired. I'm hesitant to call it truly domain-driven because we're not creating a full app ecosystem or anything like that. But basically we start, as you can see in the diagram, with the core concepts of the ADCS from which the grad students build algorithms, and then we build software on top of that, and then from that we can extrapolate tests, the drivers for the different sensors, our operating system, things like that. The methodology behind our development is largely driven by our use of GitLab. GitLab allows us to use bug and issue tracking. So basically on the GitLab itself we have specific numbered issues. We use just a basic numbering sequence that allows us to track the current bugs in the software as well as new feature development, things like that. Code changes, additions, and also the reviews before changes are merged into our develop branch are also done through GitLab. And the GitLab also contains our development methodology and the good practice documentation that I had mentioned in the previous slide. So for any code changes, we have a specific set of requirements that it must pass alongside the specific requirements for that given code. The biggest one and the first one is the testable requirements, so the TAC. Basically what this means is we have a laid out bullet point form list of everything that the code change must fulfill in a literal sense, that those who are reviewing the code can test easily to ensure that it conforms to that specific TAC. We also want issues to be able to be completed by developers such that all the TAC points are met. Then once that has happened, the code is tested and reviewed by at least 2 other developers for compliance both to the ADCS coding standards. We also want to test for runtime and efficiency if there's any really obvious mistakes with not freeing memory or using incorrect looping, things like that. And then we also obviously want to check for correctness, which is kind of how it ties in with the TAC. Typically we use 2 developers for this. If it's a very major code change or something very large scale, we'll use more than 2, sometimes up to 3 or 4. And then finally, when it conforms to steps 1, 2, and 3, we're going to merge it into the develop branch. If it doesn't, then it stays at step 3 and it's going to move back to step 2 so the developer can fix it, and it just stays in there until we can actually pass it through into the develop branch. Now the team structure of our software is somewhat agile, somewhat not. Again, the nature of developing firmware doesn't allow for a true agile methodology, but we have feature development driven by the ADCS leads, so that those being mainly our grad students, Bernardo Lobo Fernandez and Bernardo Sabino, as well as me for a bit of a software input. Then we have a Scrum Master kind of directing our 2-week long sprints. That's me currently. And then the task requirements and the task assignments and task progress are all driven by the software development team themselves. So basically what that means is we meet together every couple weeks to determine what the next 2 weeks worth of tasks are in our sprint. Our software team actually self-assigns these issues themselves. And we all agree as a team on things like the TAC, how long the issue is going to take, stuff like that, just so we can keep a democratic process and track things easily. So for conapps, we have a very basic ADCS state diagram. There's not a ton of complexity regarding how the ADCS functions in terms of its states. We basically have 3 major ones. We have the power on, so when the satellite initially boots after the 30-minute window, when we get the signal from the command and data handling board, the ADCS will be booted. And once it's booted, we're going to enter acquisition mode. So basically what that means is we're trying to acquire our attitude estimations. So what that means for us then is we're going to turn on the momentum wheel, start to detumble with that B dot diagram that was mentioned previously. We want to then boot and acquire the GPS signal, and we're going to initialize our orbital propagator and attitude estimator. Then once we've acquired our estimation, we're going to enter nominal mode. What that means for us is continuing to run the orbital propagator and estimator. Then within nominal mode, if we start to tumble again, we'll use the B-dot controller. Otherwise, we're going to use our pointing controller, which is a PD controller. We'll go into more detail with this in a bit. Here are the major diagrams regarding acquisition and nominal mode, so our two major operational modes. As you can see here in acquisition mode, it starts with turning on the momentum wheel, a check whether we are tumbling or not. We want to know if we can see the sun or not. That's what lit is. Then we want to acquire a GPS signal, turn on the orbital propagator. So at this point, we're just using our first stage, which means just using the gravity and the sun vector model for attitude estimation, or orbital propagation, pardon me. Once we've acquired that, we are going to enter the second stage of orbital propagation, which includes things like orbital disturbances for the orbital propagation as well. Once we've achieved nominal mode, so we're outside of tumbling and we've acquired our attitude, then we're going to check for GPS updates, orbital propagator resets. We're going to propagate the orbit, estimate the attitude, including sensor readings, and again, check for tumbling. So these kind of lead into each other. They're cyclic up until the point that they fail, as you can see in the previous slide, and then we'll either enter a power reset or acquisition mode again. The ADCS operating system is largely dependent on the command and data handling system operating system. For the ADCS, it's again quite a simple operating system. We have mainly cyclic task structure with the occasional update to the command and data handling board and vice versa. Task scheduling, we're going to use the free RTOS kernel, priority-based. It's round-robin scheduling. It's well proven. There's some flight heritage with that, and it's also what the command and data handling team is using. Our state machine will determine the set of tasks at any given time, and there is, as mentioned before, the free RTOS was chosen so we'd be consistent with the onboard computer command and data handling system. The state is preserved through power loss using little file system and the internal emulated EEPROM, which we got 64 kilobytes worth of application logs, telemetry information. All of that will be persisted in the file system until the OBC command and data handling requests the upload, and then little file system was chosen because it has the nice error resilience, simplicity, and it's consistent with the command and data handling board. For software error detection, we're using the TMS 570 digital windowed watchdog, as well as the software watchdog manager to monitor the individual threads for programmatic errors. As for the software structure inside of the actual operating system, it's, again, what I mentioned before, very simple cyclic sort of system. So it all starts with sensor data and orbital propagation, so the estimated and real values of where our satellite is at and what it's doing. Then that is programmed into the attitude estimator to produce an actual estimation on what our attitude is. From that, we feed a attitude estimated quaternion into the attitude controller, you can see on the far right there, to produce a control quaternion, which is then fired back into the orbital propagator, and we start all over again. So now going into the individual components of the ADCS software structure, we defined some simple requirements for them at the start of the semester. So for the orbital propagator, initially, as mentioned before, in the first stage, the orbital propagator is just going to use the gravity model for orbital propagation as well as the sun vector model. What that does then is allow us to calculate the direction cosine matrices, which allows us to convert between the different reference frames we use, like ECI, ECEF, things like that. And then the propagator is also going to compute the sun, magnetic, and atmospheric models used for the estimation and controller blocks. Once we've actually acquired our attitude, then we're going to enter the second stage of the orbital propagator, which allows us to use now not only gravity, but also the aerodynamic forces, so things like drag and solar radiation pressure for orbital propagation. The propagator will continue to compute the above DCMs. It's also going to compute the orbital perturbation forces generated by that solar radiation pressure and the aerodynamic forces of drag. And then it's also going to obtain the orbital velocity and the position by integrating the acceleration applied on the CubeSat. So then we can use that within the estimator itself. The attitude estimator is slightly more complex, so it's going to use a Kalman filter and a geometric observer to initially determine the satellite altitude. The idea behind the geometric observer is it converges extremely fast, so it gives us a good rough estimate of what our attitude is, and then we'll eventually get into the Kalman filter to produce a more refined result. So the transition between the two, we use just a 30-second watchdog. So when we hit the threshold, then we switch over to the Kalman filter. And the Kalman filter will provide us with a corrected angular rate by taking into consideration the gyroscopic biases. And for the controller, it's much more of just a math block. The attitude controller uses a detumbling controller to detumble the satellite, so that's that BDOT controller that was mentioned. The detumbling controller accepts the measured angular rate and the local magnetic field, which is sensed by the magnetometer on our board. And then when we're in the nominal mode and we're able to focus on pointing, then we're going to use the PD controller. So the PD controller produces the aired angular rate and the quaternion. It's also going to implement proportional derivative and inertial controllers to manage the actuators. And the PD controller shall control the command torques into magnetic dipole moments and combine these into a single command magnetic dipole moment. Also, the attitude controller needs to be able to deactivate when requested. So if we have a system reboot or something, we have the off switch within the operating system itself. Now taking a look at our ADCS trade-off analysis for both hardware and budgeting. We based all of our decisions around a specific trade-off philosophy, which is that we wanted to create a reliable system that attempted to save costs wherever possible, but was not allowed to affect the ability of the mission requirements themselves. So looking at our options of in-house versus completely off-the-shelf, in our research we found that there was no fully integrated off-the-shelf ADCS system available. Anything that met the actual pointing accuracy we needed would be 50,000 plus. Hyperion did offer a fully integrated ADCS, but there were no Y momentum algorithms, so it wasn't applicable for our mission. As for sensors, IMUs are simple, inexpensive, and quite easy to develop in-house. A sun sensor is quite complex, expensive, and not really feasible to test and calibrate in-house. Therefore, we wanted to go with an off-the-shelf sun sensor. And then a GPS is complex, expensive, and also not feasible to develop in-house. So both of the bottom two will be purchased off the shelf. As for actuators, momentum wheels are simple, expensive, but they're not feasible to test in-house, so that will be purchased off the shelf, whereas magnetorquers are simple and cheap. So we will be developing those in-house. Finally, for electronics, our controller is quite complex but cheap, and we will be developing that in-house. Now looking at our final options here, we were left with two final options, so in-house versus completely off the shelf. We did look at other options, but we had to discard them due to the sheer cost of a complete system. So our in-house option has a DIY controller, IMU, magnetorquer, and purchased sun sensors, momentum wheel, and GPS, whereas the completely off-the-shelf system had fully integrated hardware, but we would still need to develop the algorithms for the mission itself. When comparing costs, in-house is going to cost us $35,000 Canadian, whereas completely off the shelf would be $43,250. And considering that no ADCS fully integrated software and hardware met mission requirements and the interfacing requirements were available, at this point we will be developing the in-house solution to the ADCS system. Taking a look at the integration and interfacing of our ADCS, we're going to start with hardware here. For our mechanical board, we're using a 90 by almost 96 millimeter board. It's going to contain all of the controller hardware, including IMUs, magnetorquers, and momentum wheel. An air core wound to the acetyl frame is bolted onto the PCB. Magnetorquers are attached to the PCB using aluminum mounting brackets, and we have the momentum wheel attached to the main structure using an aluminum bracket as well. The sun sensor is bolted to the solar panel PCBs, and the GPS that our ADCS uses is actually on the command and data handling OBC. As for electrical interfaces, as mentioned in the previous diagram, we have 3V3 and 1V2 power. We're using the CAN bus for CNDH OBC communications. Our structure for communications is largely undefined at this point. For I2C, we're going to be connected to 2 sun sensors and a temperature sensor. Via SPI, we have our IMUs, our runtime clocks, and our 2 different types of memory. Then we're using pulse width modulation H bridges for our 3 magnetorquers. And finally, we have UART and JTAG headers for writing and reading to the board. The writing debugging being done through an XDS 110 JTAG debugger and reading done through the UART USB. For software interfaces, this is largely undefined for our team at this point as our operating system continues to be developed in conjunction with the CNDH operating system. Our possible options at this point are master slave and publish subscribe for the sending and receiving of information, namely GPS status and data logging and telemetry logs. For master slave, this would place the OBC in the role of the master and the ADCS in the role of the slave. This would mean having no need to periodically send data over CAN, but the period of the CNDH polling is currently unknown, so we don't know if this is feasible. As for publish subscribe, then we eliminate the need for polling. However, then we have a lot more protocol overhead and we need to acknowledge messages, and the complexity of this protocol would be much more complex. As for command sets, we're going to use a very simple predefined binary one. Currently, our required commands are software reset, getting and setting the configuration parameters, and the dumping of telemetry and application logs. Taking a look at our development and test plan for the ADCS, we have 3 stages. We got a unit test, then we have software in the loop, hardware in the loop, and finally AI and T testing. So looking at our hardware tests, we're initially struck with the issue of hardware being extremely expensive. So what that means for us is that momentum wheels and sun sensors are not likely to be present for the majority of our testing. When we get them, though, we do need to test for basic functionality and interfacing, so the ability to kind of read and write from these sensors. Unfortunately, the data we get back from them is not of particular use to us. We need to simulate that. To achieve that, we need to create engineering models for this driver testing. So again, the sun sensors, we also want to be testing the IMUs, GPS, and the magnetorquer. Further on, for the magnetorquer testing, we're going to be integrated testing it. So that means getting it on an air-bearing table so we can test the stability of its output. Software testing is a largely tiered approach. So we have unit testing followed by software in the loop testing, then hardware in the loop testing, and then AI&T in May of 2020. So currently we're in the unit testing phase where we're individually testing all the functions that go into the software while planning for our hill and sill tests. Once we start running sill in September, we're going to be running the simulated environments into our development board, manually monitoring the results and preparing for hill, which has a very similar input of a simulated environment, but this time going into a proof of concept ADCS board and also having automatic result logging. Finally, when we hit AI&T in May 2020, we'll be running the simulated environment to an actual flight hardware board with automatic trending and potentially using the Houston software for automatic reporting, depending on the compatibility and progress of that. So for software unit testing, all functions must have at least a single unit test applied to it. These tests have pretty specific criteria they need to follow. So you have a 3-part name with the name, scenario, and expected behavior of the test. And each test is structured based off the AAA pattern. So that means having objects arranged, creating and then setting them up as you would need. Then you want to act on that object that has been set up and assert that something has happened to it. We only want a single assert per test. So if you need to test multiple things in a function, you want to have more than 1 unit test. And we want to avoid logical conditions such as if, while, and the for and switch, because that defeats the purpose of the assert. Currently, we're running those tests using CUnit. However, we may consider migrating to Seedling because CUnit can only be run on our computers, and we want to eventually migrate so we can unit test on board hardware itself. Now for SIL testing, slightly more complex of a procedure. We have defined both of our parameters and results that we need to measure here for our metrics. So the parameters we're going to be feeding in are an initial quaternion representing the satellite's location and orientation. We want proportional derivative gains to be fed in and an initial angular velocity. from that, we're going to be measuring two different modes. So the detumbling and nominal pointing modes we mentioned before. In detumbling mode, our error is not considered. We're just looking to slow down the angular velocity of the satellite. So we're looking to reduce that below 0.01 radians a second, and we want a continuous decrease. As for the nominal pointing mode, we do consider pointing error at this point, so we're looking to keep it below that 10-degree error. And we also want to make sure that we're not going to start tumbling again, so that involves measuring the angular velocity for a lack of abrupt increases. We also want to monitor the magnetic dipole moment saturation when we got a low pointing error, and we're just looking for general rapid changes in the outputs that the magnetorquers use to stabilize our satellite. To accomplish this, we're going to need to run an isolated operating system on a TMS 570 launch pad. So basically this means no external communications or drivers. We're just running the ADCS as an isolated environment. We're going to be inputting it via the launch pad SI port and outputting it via just the serial USB port that is provided. The input simulated data is being produced and is completed by the Simulink model. That is then fired through serial blocks in MATLAB through the computer into the SI port of the launch pad itself. As for outputs, we're going to be monitoring those manually at this point. That means monitoring serial data via PuTTY. We're then going to parse that into a spreadsheet using a Python script, so then we can manually trend that data. And we're also going to start our process of looking into the Houston software for usage once we get into Hill. As for Hill, the metrics are almost identical. We again provide it with the identical initial parameters of a quaternion, gains, and angular velocity. And the measured outputs are also the same. So again, in detumbling mode, we're just looking for a low angular velocity that is continuously decreasing. And once we achieve our nominal pointing mode, we're looking to keep below our prescribed 10-degree pointing error, while also monitoring the angular velocity and magnetorquer outputs for any abrupt increases. However, we're also going to be measuring at this point our actuator output, so we'll have our drivers set up at this point. So we're looking to compare the command torques that we produce from our satellite software with the effective torques that are actually produced by the magnetorquers themselves to make sure the numbers are lining up. As for the tools and methodology, this is where it largely varies from software in the loop testing. We want to have a functional operating system on a hardware proof of concept board at this point. The data will be inputted via the JTAG debugger mentioned in our interfaces document, with results outputted via the USB port that is on the board itself. We also want to have simulated subsystem communications that can be outputted and received via a CAN bus. For the simulated data, this is again the same as SIL testing, so the environmental sensors will be simulated via the Simulink model. However, now we're going to be feeding them through the drivers we've created themselves to be testing to make sure that our sensor communications are working correctly. Data again is fired through serial blocks in MATLAB. Finally, our outputs are going to be monitored automatically at this point, so we want to parse and trend it via Python NumPy. And we want to obviously monitor that the predicted output is accurate to what we're expecting, and we're going to be highlighting that any sort of values that are incorrect or are concerning for us so we can adjust our system accordingly. And at this point, if the Houston system is feasible for us, we're going to be using that. We're going to take a look at the programmatic side of the ADCS, including our major timelines and other big deliverables. So it's broken up into three major phases at this point. Phase 2 is what we're currently in and starting to wrap up. Right now we're finishing off an isolated operating system. We also want to finish off our unit testing on the software, so all of the individual functions within the software itself will be tested for conformity to coding standards and efficiency and correctness. And then we're also currently developing the SIL suite itself. So the methodology by which we pass information from our simulator into the board itself, as well as the output, how we're going to capture that and parse it, things like that. Into phase 3, so this is September 2019 now, all the way until the start of 2020. We're looking to finish off that operating system. We'd like to finish the hardware proof of concept board so we can use that for Hill. And then we're actually going to run our SIL testing, make adjustments as our results come to light. And we want to develop the hill suite during this time as well. So that allows us to lead into phase 4, which is January 2020 on, which is our AI&T testing, our hill testing, and the development of flight hardware itself. So leading up to PDR, which is the end of October for us, from the software perspective, we want to update our controller to reflect these new changes that have occurred to thresholds for algorithm switching. So Bernardo Sabino has done a lot of work on improving our algorithms in the last few months, and our software has not been updated at this point to reflect the new thresholds used, so we just need to update some constant values within our software. We want to complete the software in the loop testing, so we want to have it completely up and running. So for us, that means finalization of the software in the loop, the goals document, so what the inputs and outputs we're looking for are, as well as the methodology, so how to test for those, including the tools we're going to use. These are largely defined at this point. However, we do need to agree on a finalized system. As well as mentioned before, we want to complete the isolated ADCS operating system. So this is something without any comms to outside systems or sensors, just the single software loop running inside of it. And producing some dummy communication, so things like firing the output through most likely a UART USB connection so we can parse it and check the data. And then finally, obviously, we want to actually apply the plan in the SIL documents to run the simulated data from Simulink into that isolated operating system on the dev board. So for us, that means dumping some environmental data, which already exists in Simulink, into MATLAB serial blocks, which allow us then to fire it into the development board. We want to log the pointing error, the angular rate, and the state switches manually. We're going to use PuTTY for that, just into data logs. And then we want to actually manually parse that, probably using Python, to produce some trend graphs of the outputs and obviously isolate and highlight concerning high values with error, state switching, angular rate, and other critical ADCS measurements. As well, Bernardo Sabino will continue to improve controller algorithms, testing different algorithms and thresholds. Currently, he's testing alternative attitude controllers and looking to improve the current ones we have, so the BDOT and PD controllers. As well as he wants to improve the transient procedures between the ADCS modes, namely the wheel spin-up maneuver, to be more efficient. On the hardware side, what we're looking to do before PDR is evaluate the IMU. So we want to complete that IMU driver, as well as ensure that data can be collected from the IMU. For the magnetorquers, so the control side of things, we want to begin the construction of the prototype and verify that the calculated magnetic dipole that we calculated previously is accurate, and we want to, from that, determine the final manufacturing technique, so manually winding the coils versus getting the coils winded for us. Want to create a procedure for determining if the prototype meets the design specifications outlined in the hardware section. And finally, we want to complete that test rig for the magnetorquers to actually measure the outputted dipole. For the magnetorquer driver itself, we want to evaluate the HBrid driver on a custom board. So that's going on separately from the software and the loop testing. And then we want to verify that the PWM-based driver can vary the dipole moment, produce a reasonably constant magnetic field, and adjust the dipole moment fast enough to meet any timing requirements produced by the control algorithm, which are going to become much more apparent as we run the SIL tests themselves. And finally, we want to ensure that that driver is efficient to meet the power requirements of the system as a whole. Then moving on from PDR and into CDR, what we need to complete is the hardware proof of concept board. So that means including finalized IMUs and actuators. Unfortunately, we can't expand much beyond that without an actual space environment to test things in. So things like sun sensors and other things like that. And the gravity sensors aren't of much use to us at this point, being on Earth. We want to automate our HIL software testing suite. So again, that means inputting the environmental values from Simulink or potentially STK, but we're likely to go with Simulink, onto the board itself for any set amount of time, and then have the output values also automatically logged, again, probably through PuTTY, but then automatically parsed and creating trend logs, again, with large pointing errors and angular rates highlighted. The actuator outputs should also be monitored and logged at this point. And we're also looking to set up an automatic notification system of things like system reset, satellite tumbling, and other major points of concern, such as consistent tumbling, things like that, probably over email, just so those in leadership who are concerned about the results of our hill testing can quickly check the results. And then finally, we want to evaluate our compatibility with command and data handling's Houston software, as that could be a potential use for us for the data logging and utilize it if that's possible. On the operating system side, we want a functional operating system at this point, so a OBC that can communicate with the CD and H OBC over CAN bus, as well as sending and receiving the GPS data, the telemetry, and sending error messages. Finally, we want to complete sensor and actuator drivers. Again, as I mentioned previously, we're not able to truly read the sensor and actuators for Hill. However, what we will be doing is generating the drivers, feeding simulated data into those drivers, and then firing those into our functional operating system as a kind of a simulated sensor and actuator. This is going to conclude our presentation. A big thank you to the Canadian Space Agency, NRC Canada, as well as our sponsors Rainhouse, SolidWorks, SSL, Altium, and Rocket Labs.